Hello everyone and welcome to my channel. Today I will present our group research that titled Unsupervised Anomaly Detection in Water Distribution System using Autoencoder and Isolation Forest. Now, here is the overview. We have the introduction, literature review, research question and hypothesis, methodology, expected outcomes, timelines and resources, and finally the conclusion. Now, let's begin with the introduction. Here, in modern water distribution system rely heavily on IIoT sensors and SCADA networks. While this improves automation, it also increases exposure to attacks such as cyber attacks, operational faults, and sensors failure. A major issue in this domain is the lack of labeled data. Real attacks are rare and difficult to annotate. Now, this makes supervised learning impractical. Traditional threshold based on monitoring is also no longer sufficient. Water system data is multivariate, nonlinear, and dynamic, so simple rules often miss subtle anomalies. Because of this challenge, unsupervised learning has become a promising approach. Methods like autoencoder and isolation forest detect anomalies by learning normal behavioral patterns, rather than relying on labeled attacks. In our study, we directly compare these two models under the same condition using the BATADAL dataset. Now, we're going to the literature review. On literature review, literature shows that IIoT integration increases WDS vulnerability to several physical anomalies, especially subtle shifts in flow and pressure. A key theme is lack of labeled data, which pushes research towards unsupervised methods. Now, autoencoders are effective at learning complex nonlinear dependencies and detecting anomalies through reconstruction error. LSTM-based autoencoders perform especially well for temporal sensors data. Isolation forest is known for being efficient, scalable, and suitable for high-dimensional datasets, performing best when low latency and minimal computational overhead are needed. Despite extensive research, there are few systematic head-to-head comparisons between autoencoder and isolation forest under identical setting, particularly on BATADAL. This forms our research gap. Now let's look at the research question and hypothesis. Now we're going to research question and hypothesis. On research question, our work addresses these three questions. First, how can unsupervised model detect anomalies without labeled data? Second, which model, autoencoder or isolation forest, performs better on BATADAL? And third, what accuracy efficiency trade-offs exist between two methods? And based on that question, we hypothesize that autoencoder will outperform isolation forest in detection accuracy. Second, isolation forest will require less computation and provide faster inference. And lastly, a unified experiment setup will reveal clear performance trade-offs. Now let's continue to our methodology. In data collection, we use BATADAL dataset, which contains normal operation data and test data with cyber attacks. Now it covers over 40 numerical hydraulic variables such as flow rates, pressure, tank levels, pump, and valves. Now next we're going to data preprocessing. On data preprocessing, we remove non-numerical and constant features, handled missing value using forward fill and backward fill, and standardize all numerical variables to ensure consistent model inputs. Now, next to the data partitioning. In data partitioning, we split the dataset into a normal. We split the dataset into a normal only training set, a validation set for threshold selection, and a test that includes attack intervals. We keep temporal order to preserve real-world time series behavior. Now we're going to the model development. On the autoencoder model, the autoencoder model consists of an encoder, bottleneck, and decoder. It reconstructs normal data and flags anomalies when the reconstruction error is high. It captures nonlinear sensor relations but requires more training time and computation. And next is the isolation forest model. Now, the isolation forest isolates anomalies through random feature splits. And anomalous points are isolated more quickly and produce short path lengths. Now, it is extremely fast and lightweight, making it suitable for real-life environment, but it is less effective for subtle nonlinear anomalies. Next is the evaluation. Now, we evaluate performance using precision, recall, and F1 score based on the attack labels in the BATADAL dataset. And next is the comparative analysis. Here are the key findings. First, accuracy. The autoencoder achieves high precision, recall, and F1 score. And in terms of robustness, autoencoder handles correlated and noisy data consistently. In terms of robustness, autoencoder handles correlated and noisy data more consistently. Now, isolation forest performs less reliably. Isolation forest performs less reliably in this condition. And lastly, the efficiency. Now, isolation forest is significantly faster and requires fewer computational resources. However, compared to autoencoder, which is slower but provides stronger detection performance. Overall, autoencoder is for better accuracy, isolation forest for better real-time efficiency. Now we're going to expected outcomes. Now, autoencoder is expected to achieve stronger anomaly detection accuracy due to its ability to capture nonlinear direct relationship. Now, isolation forest should deliver faster inference and minimal resource usage, making it suitable for real-time or edge deployments. Now, the study we highlight practically trade-off between accuracy and efficiency, helping system engineers choose the right model. Now, results will support better cybersecurity, monitoring strategy for water distribution, and other industrial control system. Now, in conclusion, unsupervised anomaly detection is essential for water system where labeled attacks are limited. The autoencoder provides stronger detection accuracy, while the isolation forest offer fast and efficient performance. By comparing both models under identical conditions, our study fills an important research gap and supports better by monitoring and cybersecurity for industrial water system. That's today for my research group presentation. Thank you for listening. Bye-bye.